Tonight, we're going to watch the sun die. Not in a metaphor, not in a science fiction scenario, in a scientifically precise, step-by-step account of exactly what will happen to our star over the next 5 billion years. And then, because the death of the sun is not the end of the story, we're going to keep going. Past the death of the sun, past the death of all stars. Into the universe's far future, into eras of time so vast that they have no human name, where the rules of physics still operate, but the cosmos looks nothing like the one we inhabit tonight. Before we begin, 3 numbers, just 3. Then we will spend the rest of tonight explaining them. In approximately 1.1 billion years, the sun will be about 10% brighter than it is today. That is not a large change by stellar standards. But on Earth, 10% more solar luminosity is enough to begin the irreversible evaporation of the world's oceans. Not quickly, over tens of millions of years. But once it begins, it will not stop. The water that covers 71% of this planet's surface, that makes it blue from space, that makes complex life possible, will leave and will not return. In approximately 5 billion years, the sun will exhaust the hydrogen fuel at its core and begin expanding into a red giant. During this expansion phase, it will grow to roughly 200 times its current diameter. The orbit of Mercury will be inside the sun. Venus will be incinerated. Whether Earth survives as a separate body is genuinely uncertain. Models disagree by margins that include Earth being swallowed and Earth narrowly surviving, depending on the rate of the sun's mass loss and the corresponding change in Earth's orbital radius. In approximately 10 to the power of 100 years, 1 Google years, a number so large that writing out all its zeros would take more paper than exists on Earth, the last black hole in the universe will finish evaporating. After that moment, the universe will contain nothing but a diffuse, cold, perfectly uniform gas of photons and leptons, expanding forever, never again forming a structure of any kind. This is the end state of everything. Not a collapse, not a crunch, a slow, perfect, absolute silence. We will get to all of it tonight. If you've never thought carefully about what the sun actually is, what it will do, and what comes after, this is the night. Because it turns out that the death of the sun is one of the most detailed, most precisely understood, and most consequential things physics can describe. We know more about what will happen to the sun in 5 billion years than we know about what will happen to most things in 50 years. Stars are predictable. The physics is clean. The story is extraordinary. Before we begin, if you find yourself here regularly, if this is where you come when you need something real and slow and deep before sleep, please hit like and subscribe to Calm Theory for Sleep. It takes 3 seconds, and it helps this channel reach more people who need exactly this. Now let us start at the beginning. The sun is 4.6 billion years old. It formed from a cloud of gas and dust, a molecular cloud, a region of the galaxy where hydrogen and helium and traces of heavier elements had accumulated over billions of years of prior stellar evolution. That collapsed under its own gravity roughly 4.6 billion years ago. As the cloud collapsed, it heated up. The center grew denser and hotter until, at a temperature of about 15 million Kelvin and a density about 150 times that of water, the protons at the core were moving fast enough and close enough together that they began fusing. Hydrogen nuclei, pressed together by gravity and moving at thermal speeds, overcame their electromagnetic repulsion and merged. Helium was produced. Energy was released. The sun ignited. That moment of ignition is called zero-age main sequence. The sun, at zero-age main sequence, was slightly less luminous than it is today, about 70% of its current brightness. In the 4.6 billion years since, it has brightened by about 30%, slowly and continuously, as the helium ash at its core has increased the mean molecular weight of the core material, causing it to contract slightly and heat up, which increases the rate of fusion in the shell around the core. The Sun is currently roughly halfway through its main sequence lifetime. It has about 5 billion years of hydrogen burning ahead of it. After that, everything changes, and the changes happen on a timeline that is specific enough and strange enough that we can trace it step by step. That is what tonight is. A step-by-step account of the end of everything familiar. Narrated slowly, so you can hold each step before the next one arrives. The Sun is, at this moment, converting approximately 600 million tons of hydrogen into helium every second. This happens through a chain of nuclear reactions called the proton-proton chain. Two protons fuse to form a deuterium nucleus, releasing a positron and a neutrino. The deuterium nucleus fuses with another proton to form helium-3, releasing a gamma ray. Two helium-3 nuclei fuse to form helium-4, releasing two protons back into the mix. The net result, 4 hydrogen nuclei become one helium nucleus. And the helium nucleus has slightly less mass than the 4 hydrogen nuclei combined. That missing mass, about 0.7% of the original, is converted directly to energy according to Einstein's equation E equals mc squared. The speed of light is approximately 300,000 kilometers per second. The speed of light squared is 90 billion kilometers squared per second squared. The energy released per unit mass is therefore enormous, and with 600 million tons of hydrogen fusing every second, the total power output of the Sun is approximately 3.8 times 10 to the power 26 watts. That is the luminosity of the Sun, 3.800 septillion watts. Earth intercepts about 1/2 billionth of this output. That 1/2 billionth, the solar constant at Earth's distance, averaged over the day-night cycle and accounting for reflection, drives every weather system, every ocean current, every photosynthetic reaction, every living thing on this planet. All of terrestrial biology runs on a thin sliver of the Sun's output, the rest of which streams outward into space in all directions, heating nothing, illuminating nothing, a colossal and mostly wasted furnace. The hydrogen at the Sun's core, the roughly 35% of the Sun's total mass that is hot enough and dense enough to undergo fusion, is being depleted at that rate of 600 million tons per second. The helium ash accumulates. The core gradually changes composition, and as it changes, the Sun gradually brightens. Because the increased mean molecular weight requires the core to contract and heat slightly to maintain pressure equilibrium, which slightly increases the fusion rate, which slightly increases luminosity. This process has been going on for 4.6 billion years. It will continue for approximately 5 billion more years. During that time, the Sun will brighten from its current luminosity to about twice its current luminosity. That brightening is slow, barely perceptible on any human timescale. But on geological and biological timescales, the brightening is decisive, and we can trace exactly when it begins to matter. The Sun's core right now is a sphere about 25% of the Sun's radius, roughly 170,000 kilometers across. Its temperature is 15.7 million Kelvin. Its density is 150 grams per cubic centimeter. It is so dense that a photon of light produced at the core takes approximately 100,000 years to work its way out to the surface through the process of repeated absorption and re-emission. The sunlight reaching your eyes tonight left the sun's surface 8 minutes ago, but the energy it carries was generated in fusion reactions that began 100,000 years ago, in the core of a star that predates all recorded human history. The surface of the sun, the photosphere, is at a temperature of about 5,778 Kelvin, which corresponds to the yellow-white color we observe. Above the photosphere, a thin region called the chromosphere, and then the extended corona, at temperatures of 1 to 3 million Kelvin, hotter than the surface by a factor of hundreds. Heated by mechanisms still not completely understood, form the outer envelope that bleeds into the solar wind. This is the sun as it is now, middle-aged, stable, reliable. The same sun that warmed the Jurassic, that witnessed the first land plants, and the first vertebrates, and the first hominids, and the first cities, and the first rockets. And the same sun that, in geological terms, very soon will begin the process that ends all of this. The first major milestone in the sun's aging is not the death of the sun, it is the death of Earth's oceans, and it comes long before the sun enters its death phase. In approximately 1.1 billion years, the sun will be about 10% brighter than it is today. A 10% increase in solar luminosity does not sound catastrophic, but Earth's climate system is extraordinarily sensitive to small changes in the solar input, and the consequences of a 10% increase are not proportional to the size of the change. They are, in fact, effectively irreversible. The mechanism is called the moist greenhouse effect. As the sun brightens, Earth's surface temperature rises. Higher temperatures increase the rate of evaporation from the ocean surface. More water vapor enters the atmosphere. Water vapor is itself a greenhouse gas. In fact, it's the dominant greenhouse gas in Earth's atmosphere, responsible for more warming than carbon dioxide or methane. More water vapor means more warming, which means more evaporation, which means more water vapor. This is a positive feedback loop. The critical threshold occurs when the stratosphere, the upper layer of the atmosphere, becomes wet. Right now, the stratosphere is extremely dry. Water vapor condenses and rains out before it reaches stratospheric altitudes. This is important because water in the stratosphere is destroyed by ultraviolet radiation from the sun, which splits the water molecule into hydrogen and oxygen. The hydrogen, being light, escapes to space. When the stratosphere is dry, this process only very slowly removes water from Earth. But when the stratosphere becomes moist, when the warming is severe enough that water vapor penetrates to stratospheric altitudes in large quantities, the loss of hydrogen to space accelerates dramatically. Earth begins to irreversibly lose its water. This process will unfold over tens of millions of years, not overnight. The oceans won't boil suddenly. What will happen is a gradual, accelerating desiccation. The oceans will shrink. The land masses will expand. The water vapor concentration in the atmosphere will initially increase as the oceans evaporate, creating a superhumid world with a powerful greenhouse effect and surface temperatures far above what we experience today. And then, over tens of millions of years, as hydrogen continues escaping to space, the total water inventory of the planet will decline. The oceans will not boil away in the conventional sense. They'll be lost to space, hydrogen atom by hydrogen atom, over geological timescales. In parallel with the moist greenhouse onset, another process will have already made complex life difficult or impossible. The carbonate-silicate cycle, the geological process by which carbon dioxide is drawn out of the atmosphere by chemical weathering of rocks, deposited in the ocean as carbonate sediments, and eventually returned to the atmosphere by volcanic outgassing, is temperature dependent. As Earth warms, the weathering rate increases, pulling more carbon dioxide from the atmosphere. In about 600 million years, the atmospheric CO2 concentration will fall below the threshold needed for C3 photosynthesis, the biochemical pathway used by most plants on Earth today. Grasses, trees, most flowering plants, most of the photosynthetic base of terrestrial food webs. They will die. C4 photosynthesis, a more efficient pathway used by some grasses and crops like corn and sugarcane, can survive somewhat lower CO2 concentrations. But it too has a lower limit, and the continuing decline of atmospheric CO2 will eventually eliminate C4 plants as well. In roughly 800 million years, terrestrial photosynthesis will effectively cease. Without photosynthesis on land, the oxygen content of the atmosphere will begin to decline. Complex, oxygen-breathing animal life will become impossible. What will remain in the period between the death of complex life and the death of the oceans is microbial. Bacteria and archaea, the deep-dwelling, chemosynthetic, extremophilic forms of life that have survived every mass extinction in Earth's history, will continue in the deep ocean and in hydrothermal vents, thriving in conditions that kill everything else. The last common ancestor of all life on Earth was probably a microbe living near a hydrothermal vent. The last life on Earth will probably be a microbe living near a hydrothermal vent. There is a symmetry there that's worth sitting with. Life, complex, multicellular, oxygen-breathing life, has existed on Earth for about 600 million years. We are approximately at the midpoint of complex life's tenure. The window during which a visitor from another star system would look at Earth and see complex organisms is roughly 1.2 billion years wide. We are inside that window, near its middle. Once it closes, it will not open again. The Earth in 1.1 billion years will still be recognizably a planet. It will still have continents and a solid surface. The sun will still rise and set, but the world it illuminates will be alien by every biological standard. Hotter, drier, sparsely populated by extremophile microbes. Its oceans shrinking, its skies altered, its long tenure as a cradle of life approaching its end. Venus today has a surface temperature of approximately 465 degrees Celsius, hot enough to melt lead. Its atmosphere is 96% carbon dioxide, with an atmospheric pressure 90 times that of Earth's surface. Its clouds are made of sulfuric acid droplets. No liquid water exists anywhere on its surface, and there's compelling evidence that Venus may have had oceans in the distant past. A warm, wet world that underwent a runaway greenhouse effect and became the inferno it is today. Earth, in roughly 2 to 3 billion years, will look very much like Venus looks today. The process will be driven by the continued brightening of the sun and the progressive loss of atmospheric water. As the oceans decline, the remaining water is concentrated into an increasingly humid atmosphere. The greenhouse warming intensifies. Surface temperatures rise above 100 degrees Celsius in equatorial regions, then globally. The last of the surface liquid water evaporates. The carbonate rocks that have stored billions of years' worth of carbon dioxide begin releasing it back into the atmosphere as temperatures rise. A process called decarbonation, which requires temperatures above about 900 degrees Celsius to occur rapidly, but which proceeds gradually at lower temperatures over geological time. The surface of Earth in this era will be geologically active. The mantle will still be warm from primordial heat and from the ongoing decay of radioactive elements: uranium, thorium, potassium, 40, that were incorporated into Earth at formation. Volcanoes will still erupt. Tectonic plates may still move, though the rate of geological activity declines as the interior cools over geological time. But there will be no water to drive the rock cycle, no oceans to absorb CO2, no silicate weathering to regulate the climate. The planet's self-regulating climate system will have broken down completely. The atmospheric pressure will rise as CO2 released by volcanic outgassing accumulates. Surface temperatures will rise toward 300, 400, 500 degrees Celsius. The surface rock will glow dull red at the highest temperatures. The atmosphere will be a thick, hot, acidic mixture of CO2, SO2, and nitrogen, with traces of water vapor still present, but in quantities too small to condense. This is not speculation. We can see this process in its current state by looking at Venus. We don't fully understand whether Venus underwent its transition naturally, due to its slightly closer orbit and consequent higher solar flux, or whether it had a triggering event. But the end state of a runaway greenhouse effect is well characterized, and Earth is on the same trajectory, following Venus into that end state on a timescale of a few billion years. The solar system, in 2 to 3 billion years, will be a different place. Mars, slightly farther from the Sun, will have warmed significantly. The Martian CO2 atmosphere will have thickened somewhat as permafrost and polar caps sublimate. Mars might, in this period, have seasonal liquid water, a brief, ironic moment when the planet that was wet in the early solar system becomes wet again for a short geological era, just as the planet that was previously wet becomes permanently dry. The asteroid belt will be unchanged in its broad structure. The outer solar system, Jupiter, Saturn, Uranus, Neptune, will have changed only slightly, their massive bulk largely immune to the Sun's gradually increasing luminosity. The Jovian moons, Europa, Ganymede, Callisto, will have warmed slightly. The ice shells of Europa and Enceladus may have thinned. The subsurface oceans beneath those ice shells, currently maintained by tidal heating, may have been augmented by surface heating. For a brief geological window, the ice moons of the outer solar system may be more hospitable to liquid water at the surface than at any other point in their history. Life, if any persisted in those subsurface oceans, might find a temporary improvement in conditions. Or it might find that the ice insulation that protected it is gone, and the radiation environment has changed. We don't know. The ice moons of Jupiter and Saturn are among the great unknowns of our solar system's future. Meanwhile, Earth, once the garden of the solar system, the only planet we know to have hosted life, will be completing its transformation into a sterile, furnace-hot, acid atmospheric world. Still orbiting, still a planet, but recognizable as Earth in no sense that matters. The main sequence is the long, stable phase of a star's life, during which it burns hydrogen at its core. Our Sun has been on the main sequence for 4.6 billion years. It has approximately 5 billion years of hydrogen burning remaining. At the end of those 5 billion years, something fundamental changes. The hydrogen at the core runs out. Not all the hydrogen in the Sun, the outer layers, are still hydrogen-rich. But the hydrogen in the core, the dense, hot, fusion-capable core, is exhausted. Helium, the ash product of billions of years of hydrogen fusion, now fills the center of the star. And helium, at the temperatures and densities present in the current solar core, cannot fuse. The temperature required to initiate helium fusion, the triple alpha process, in which 3 helium-4 nuclei fuse to form carbon-12, is about 100 million Kelvin. The current solar core temperature is about 15 million Kelvin, a factor of 7 too cool. With no fusion energy production at the core, the pressure that was supporting the core against gravity disappears. The core begins to contract. Gravitational potential energy converts to heat. The core gets hotter and denser as it contracts, not because fusion is occurring, but because gravity is compressing it. Meanwhile, the outer layers of the Sun are doing something different. The shell of hydrogen just outside the helium core, still at fusion temperatures, begins burning more intensely than before. The contraction of the core releases energy that heats the surrounding shell. Shell burning is actually more vigorous than core burning was. The Sun's luminosity begins to rise. But the energy doesn't just come out as more light. It also goes into inflating the outer layers. The Sun begins to expand. Not quickly on a human timescale. This expansion occurs over hundreds of millions of years. But inexorably, the Sun grows. Its surface area increases. And as it grows, its surface temperature actually decreases. The same total power spread over a larger area means lower temperature per unit area. The Sun's color shifts. It was white-yellow on the main sequence. As it expands and cools, it becomes more orange, then red. The Sun is becoming a red giant. At the peak of the red giant phase, roughly 5.4 billion years from now, the Sun will have expanded to about 200 times its current diameter. Its surface temperature will have dropped to about 3,000 to 4,500 Kelvin. Its luminosity will have increased to about 2,700 times its current value. Not 10% more, 2,700 times more. The visual appearance of the Sun from the inner solar system will be unrecognizable. It will fill a large fraction of the sky. It will be enormous, a bloated, dim red disk dominating the view in every direction from Earth's orbit. If Earth still exists at this point, and we'll get to whether it does, it will be at the center of the Sun's extended outer atmosphere, bathed in a diffuse hot plasma. What happens to the inner planets during the red giant expansion is the subject of detailed modeling, and the details matter. Mercury is certainly destroyed. Its orbit at 0.39 AUS is well within the expected maximum radius of the red giant's Sun, which will extend somewhere between 1.0 and 1.5 AUS depending on the model. Mercury will be engulfed long before the Sun reaches its maximum size. Venus, orbiting at 0.72 HUM, is almost certainly destroyed. The Sun's outer layers will expand past Venus's orbit. Whether Venus is truly engulfed in the sense of being inside the photosphere, or whether it orbits in the super-extended, ultra-thin outer atmosphere of the red giant, is a question of definition. In practical terms, Venus at 0.72 AGO, during the peak red giant phase, is inside the Sun. Earth's fate is less certain, and this uncertainty is interesting. Earth orbits at 1.0 AU. The Sun's maximum radius during the red giant phase is expected to be between 1.0 and 1.5 ATU. Earth might be just outside the Sun's maximum extent, or just inside it. There's a complicating factor that works in Earth's favor: mass loss. During the red giant phase, the Sun loses mass. The intense radiation and weak surface gravity of the inflated outer layers drives a strong stellar wind, far stronger than the current solar wind. Over the red giant phase, the Sun may lose 30 to 40% of its total mass. As the Sun loses mass, its gravitational pull decreases. A planet in a gravitational field that's getting weaker gradually migrates outward. Its orbit expands. Earth's orbit, in response to the Sun shedding mass, will expand from its current 1.0 AU to perhaps 1.3 to 1.5 astronaut. If Earth's orbit expands fast enough, if the Sun sheds mass quickly enough, Earth could end up at 1.5 ATU or beyond, safely outside the Sun's maximum radius. If the mass loss is slower, or if tidal interactions between Earth and the red giant's outer envelope are strong, these interactions can drain orbital energy and cause Earth to spiral inward rather than outward. Earth could be dragged into the expanding Sun. Different models give different answers. A 2008 study by Schroeder and Conan Smith calculated that Earth would be engulfed, even accounting for mass loss, because tidal deceleration would dominate. Other models suggest Earth survives barely. The scientific community has not reached consensus. What is certain is that Earth, whether engulfed or not, will be utterly uninhabitable long before the red giant phase. The surface will have been stripped of all volatiles, all water, all atmosphere. The surface rock will be incandescent. If Earth survives as a body, it will be a charred, airless, radiation-baked rock orbiting a star 2,700 times more luminous than today's Sun. While the Sun is in the red giant phase, the helium core is contracting, heating up, getting denser. For millions of years, the core heats without igniting. The helium is there, but it's not yet hot enough to fuse. The core is in a state called electron degeneracy. At the extreme densities achieved by the contracting helium core, quantum mechanical effects take over. Electrons are forced into their lowest possible energy states, creating what's called degeneracy pressure. In a degenerate gas, the pressure doesn't depend on temperature the way it does in a normal gas. You can heat a degenerate gas without increasing its pressure. The usual safety valve that regulates normal stars is gone. Eventually, the contracting helium core reaches approximately 100 million Kelvin. The triple alpha process ignites. 3 helium-4 nuclei, moving at high thermal speed, fuse in rapid succession. Helium 4 plus helium-4 forms beryllium-8, which is unstable and lasts only about 10 circumflex, 16 seconds. But in that brief window, a third helium-4 can collide with the beryllium-8 to form carbon-12, and carbon-12 is stable. This is the triple alpha reaction, and it is the source of all the carbon in the universe. When helium ignites in the degenerate core, the energy released does not expand the core. In a normal gas, releasing energy would increase pressure, which would push the material apart, which would cool it down, a self-regulating thermostat. In a degenerate gas, there's no such regulation. The energy goes into heat, not expansion. The temperature rises. Higher temperature means faster triple alpha reactions, which release more energy, which raises the temperature further. A runaway ignition in the degenerate helium core. This is called the helium flash. In a matter of hours, the energy released in the core is comparable to the sun's entire luminosity over millions of years. The flash is not visible from outside the star. The energy is absorbed by the overlying layers before it reaches the surface. But in the core, something dramatic is happening. The temperature rises until the electron degeneracy is lifted, and the core begins behaving like a normal gas again. At that point, the temperature pressure regulator is restored, the runaway stops, and the star settles into a new, stable phase of helium burning at the core. After the helium flash, the sun will be on what astronomers call the horizontal branch, a stable phase of helium core burning that lasts about 100 million years. During this phase, the sun will actually shrink slightly and brighten slightly, compared to the peak red giant, settling into a smaller, hotter, more stable configuration. If Earth survived the red giant phase, it would experience a somewhat less extreme environment during the horizontal branch. Not habitable, the planet is still an irradiated rock, but slightly less irradiated than at the red giant peak. During the horizontal branch, the sun burns helium at its core and accumulates carbon and oxygen ash. When the helium at the core runs out, the situation repeats. The core contracts. A helium-burning shell ignites around the carbon-oxygen core, and the sun expands again into what's called the asymptotic giant branch, a second red giant phase, sometimes more luminous and more extended than the first. On the asymptotic giant branch, the sun experiences thermal pulses, quasi-periodic episodes of explosive helium shell burning, separated by periods of hydrogen shell burning. Each pulse drives a powerful wind from the outer layers. The sun loses mass rapidly. The outer layers are gradually stripped away, and the remaining object, the dense carbon-oxygen core, surrounded by a thin shell of helium and then a thin shell of hydrogen, is exposed to view. This exposed core is a white dwarf, and the material that was expelled from the outer layers, that becomes a planetary nebula. A planetary nebula has nothing to do with planets. The name is a historical accident. When early telescopes resolved these objects as roughly circular glowing clouds, some astronomers thought they resembled the disk of a planet. They don't. A planetary nebula is the ghost of a star's outer layers, illuminated by the hot stellar remnant at the center. When the sun completes the asymptotic giant branch phase and sheds its outer layers, those layers expand outward at roughly 20 to 30 kilometers per second. The material, hydrogen and helium, enriched with the carbon and oxygen that were dredged up from the interior by convective mixing during the giant phases, spreads into a shell around the exposed stellar core. Initially, this shell is too cool and too diffuse to glow. But the exposed core, the newly formed white dwarf, is extremely hot. Immediately after exposure, the white dwarf has a surface temperature of over 100,000 Kelvin. At 100,000 Kelvin, the white dwarf emits copious ultraviolet radiation. This UV radiation ionizes the surrounding shell of expelled gas. The ionized gas glows. The planetary nebula is born. The nebula expands. Over thousands of years, it spreads from a region a few tenths of a light year across to a region a few light years across. As it expands, it becomes more diffuse. After about 10,000 to 50,000 years, it has diluted to the point where the glowing gas is no longer distinguishable from the surrounding interstellar medium. The planetary nebula dissipates. What remains is the white dwarf at the center, slowly cooling. The planetary nebula that the sun will produce will be roughly comparable to some of the most beautiful objects we can observe today. The Ring Nebula in the constellation Lyra, the Helix Nebula in Aquarius, the Cat's Eye Nebula in Draco, the Butterfly Nebula in Scorpius. These are all planetary nebulae from other stars, other suns that have gone through the same process. We can photograph them in extraordinary detail. We know exactly what our sun's death will look like, because we can see the same death happening to dozens of nearby stars right now. The material expelled in the planetary nebula does not disappear. It joins the interstellar medium, the gas and dust between stars. It is enriched with carbon and oxygen from the sun's interior, elements forged in helium burning over millions of years, and never before part of the interstellar environment. This material, this specific selection of elements in these specific proportions, will be incorporated into future molecular clouds, future star-forming regions, future stars and planets. The carbon in the sun's planetary nebula will, billions of years later, become the carbon in new planets and potentially in new life. The sun will seed the galaxy with the products of its nuclear burning, just as previous stars seeded the cloud that formed our solar system. If any intelligent life exists in the galaxy in 5 to 6 billion years, somewhere else, around some other star, in some other solar system, they may observe the nebula that was once our sun. They will see a beautiful glowing shell of gas. They will measure its spectrum and find carbon and oxygen and nitrogen in specific abundance ratios. They will note the hot white dwarf at its center. They will not know that the system produced life. They will not know that for roughly 1 billion years, the third planet from the star was covered in liquid water and populated by living things. They will see only the nebula and make their measurements and move on. The planetary nebula phase lasts tens of thousands of years, a blink in astronomical time. After the nebula disperses, the white dwarf at the center begins the longest phase of all, a cooling that will last not millions of years, not billions of years, but trillions. The white dwarf that the sun leaves behind will have a mass of approximately 0.54 solar masses, about 54% of the sun's current mass. The other 46% will have been expelled in the stellar wind during the giant phases and in the planetary nebula. The white dwarf will have a radius of approximately 7,000 kilometers, roughly the size of Earth. Think about that for a moment. The Sun today has a radius of about 696,000 kilometers. The white dwarf will be 0.54 solar masses, compressed into a volume roughly the size of Earth. The density of the white dwarf will be approximately 1 million times the density of water. A teaspoon of white dwarf material would weigh approximately 15 tons on Earth. The white dwarf is made primarily of carbon and oxygen, with a thin surface layer of hydrogen and then helium. It is not undergoing any nuclear fusion. It is not generating any energy from internal reactions. It is simply a hot ember, an object that was enormously hot at formation and is now slowly radiating away that heat into space. Its only energy source is the thermal energy stored in its ions and the degeneracy energy of its electrons. White dwarfs cool according to well-understood physics. The rate of cooling depends on the white dwarf's mass, composition, and luminosity. Initially, the newly formed white dwarf cools rapidly, losing most of its initial luminosity in the first billion years or so. Then the cooling slows, because as the white dwarf becomes cooler and dimmer, it radiates less energy per second, and the cooling rate decreases. Over the first billion years after formation, the Sun's white dwarf will cool from its initial temperature of around 100,000 Kelvin to something in the range of 20,000 to 30,000 Kelvin. Still very hot. Still glowing blue-white. Still much hotter than the current sun. It will be far less luminous than the current sun. A tiny, hot, dense sphere emitting light across a small surface area. Over the next few billion years, it cools to 10,000 Kelvin. Still hot. The White Dwarf, about 6 billion years after formation, roughly 11 billion years from now, will be at a temperature comparable to the current sun's surface, glowing yellow-white. But because it's only the size of Earth, its luminosity is tiny, perhaps 1% of the current sun's luminosity. The cooling continues. After about 10 billion years as a white dwarf, the sun's remnant will be at roughly 6,000 Kelvin, slightly cooler than the current sun. After 15 billion years, 4,000 Kelvin. After 30 billion years, 2,500 Kelvin. The white dwarf cools through yellow, through orange, through red, and finally dims below the threshold of any optical detection. This process takes extraordinarily long. The current age of the universe is 13.8 billion years. The universe is not old enough to have produced any fully cooled white dwarfs. Every white dwarf in the observable universe today is still glowing, still above absolute zero by thousands of degrees, because they simply haven't had time to cool completely. The oldest white dwarfs we can observe in the ancient globular cluster Messier 4 are about 12 to 13 billion years old, and they have cooled to roughly 2,500 to 4,000 Kelvin. Still warm, still glowing. After roughly 100 trillion years, 10 circumflex 14 years, about 7,000 times the current age of the universe, the sun's white dwarf will have cooled below the threshold of visible light emission. It will emit only infrared radiation, then microwave radiation, then nothing detectable. It will be a cold, dark, inert sphere of carbon and oxygen, about the size of Earth, slowly drifting through the interstellar medium. Still there, still intact, simply cold. At this point, it is sometimes called a black dwarf. But here is the critical note. No black dwarf is known to exist, and none can exist yet. The universe has not been around long enough for any white dwarf to have cooled completely. The first black dwarfs will form in something like 100 trillion years from now. The sun's remnant will become a black dwarf sometime around 100 trillion years from now. But the universe in 100 trillion years is a very different place from the universe today. And to understand what the sun's death means in the full cosmic context, we need to follow the timeline not just through the sun's life, but through the universe's. The sun's death is not the end. It's not even close to the end. We are living, right now, in what cosmologists call the stelliferous era, the era of stars. The period of cosmic history during which hydrogen gas is being converted to helium in stellar cores across the observable universe, when galaxies are lit by the glow of billions of burning suns, when the night sky is full of light from active stellar objects. The stelliferous era began about 150 million years after the Big Bang, when the first stars ignited from the primordial hydrogen and helium gas. We are currently about 13.8 billion years into it. It will end in approximately 100 trillion years, 10 circumflex 14 years. The reason it ends is straightforward. Stars consume hydrogen. The supply of hydrogen in any given galaxy is finite. As stars burn their hydrogen and die, returning some of it to the interstellar medium as planetary nebulae and stellar winds, Not all of it is recycled. Some is locked in white dwarfs and neutron stars and black holes. Some is expelled in supernova explosions at high enough velocities to escape galaxies entirely. Gradually, over trillions of years, the available hydrogen for star formation declines. New stars are forming less frequently already. The star formation rate of the universe peaked about 3.5 billion years after the Big Bang and has been declining since. The Milky Way currently forms about 3 solar masses worth of new stars per year. In 100 billion years, this rate will have declined by roughly another factor of 10. In 1 trillion years, new star formation will be essentially negligible. The existing stars will simply burn out, one by one. The longest-lived stars are the smallest ones. The smallest stars on the main sequence, called M-dwarf or red dwarf stars, have such low mass and such low core temperatures that they burn their hydrogen extraordinarily slowly. A red dwarf with a mass of about 10% of the Sun's mass has a main sequence lifetime of approximately 10 trillion years. 10 circumflex 13 years. More than 700 times the current age of the universe. The lowest mass red dwarfs, at about 7 to 8% of a solar mass, just barely massive enough to sustain hydrogen fusion at all, have lifetimes approaching 100 trillion years. 10 circumflex 14 years. When the Sun has been a black dwarf for 90 trillion years, there will still be some red dwarf stars quietly burning in the galaxy. In about 100 trillion years, the last red dwarf will exhaust its fuel. It will expand briefly, lose its outer layers, and leave behind a white dwarf far less massive than the Sun's remnant, perhaps 10 to 15% of a solar mass. This tiny white dwarf will begin its own cooling, measured not in billions of years, but in trillions. After the last red dwarf dies, the stelliferous era is over. The universe enters the degenerate era. The degenerate era is defined by what remains: white dwarfs, neutron stars, and brown dwarfs. Objects that failed to achieve sustained fusion but contain matter in degenerate states. Brown dwarfs are objects too massive to be planets, but too low mass to ignite hydrogen fusion. They glow faintly from their residual heat for trillions of years, then go cold and dark. White dwarfs do the same on even longer timescales. Neutron stars, the densest ordinary matter in the universe, cool over similar timescales. The galaxy in the degenerate era is dark. Not completely. The white dwarfs and cooling brown dwarfs still emit some infrared radiation. But the blazing, light-filled universe we inhabit, with its brilliant stars and colored nebulae and bright galaxy centers, will be gone, replaced by a cold, dim scattering of small, dark, dense objects, drifting through an ever-expanding space. The degenerate era lasts from about 10 circumflex 14 years to about 10 circumflex 40 years, when proton decay, the hypothetical decay of the proton into lighter particles, predicted by some grand unified theories, begins to dissolve all ordinary matter. If proton decay occurs at the predicted rate, every proton in every white dwarf, every neutron star, every cold rock and dead planet will eventually decay. The timescale is approximately 10 circumflex, 32 to 10 circumflex, 40 years. During the proton decay epoch, the white dwarfs and neutron stars slowly evaporate, not through heat or radiation, but through the statistical decay of their constituent protons. The process releases energy, primarily positrons and neutrinos, as well as pions, that then decay to photons. White dwarfs, their protons decaying, slowly lose mass and shrink, eventually leaving behind nothing. Or, if the proton doesn't decay, they persist indefinitely as cold black dwarfs, accumulating extremely rare quantum tunneling events that very slowly transform their composition. The degenerate remnants of 100 trillion years of stellar evolution dissolve back into fundamental particles. The universe becomes even simpler, and then the black holes take over. After the degenerate era, if proton decay has proceeded and dissolved most ordinary matter, the universe enters what Adams and Laughlin, in their landmark 1997 paper, a dying universe. The long-term fate and evolution of astrophysical objects, called the black hole era. This era runs from approximately 10 circumflex 40 years to 10 circumflex 100 years. By this point in cosmic history, black holes are the only significant structures remaining. The galaxies are gone, or rather, the stars that compose them are gone. And what remains are the black holes that formed from the most massive stellar deaths and from the mergers of stellar remnants over the previous eons. Galaxies themselves, as gravitationally bound structures, may have already partially dissolved. In the extremely long timescales of the degenerate era, gravitational scattering events, rare but accumulating over trillions of years, gradually eject stars and stellar remnants from galaxies. Over 10 circumflex 19 to 10 circumflex 20 years, most stars are ejected from their galaxies, leaving behind only the central supermassive black holes. The supermassive black holes are then the primary structures in the universe. The one at the center of the Milky Way, Sagittarius A, currently 4.15 million solar masses, will have grown somewhat by then, consuming whatever gas and stellar material fell into it over the previous eons. Other black holes, former stellar remnants, dot the universe in enormous numbers. All of them are slowly, imperceptibly evaporating. Hawking radiation. In 1974, Stephen Hawking showed that black holes are not perfectly black. At the event horizon, quantum mechanical effects cause pairs of virtual particles to become real, with one particle escaping and the other falling in. The escaping particle carries energy, reducing the black hole's mass. The rate of mass loss depends on the black hole's mass. Smaller black holes radiate more intensely and evaporate faster. The timescale for a stellar mass black hole to evaporate completely is approximately 10 circumflex, 67 years. For a supermassive black hole like Sagittarius A, the evaporation time is approximately 10 circumflex, 87 years. For the most massive black holes known, those with 66 billion solar masses, like TON 618, the evaporation time is on the order of 10 circumflex, 100 years. During the black hole era, the universe is not completely empty of energy. The Hawking radiation from evaporating black holes provides a faint, ultra-low energy radiation field. Each black hole is surrounded by an extremely dim glow of Hawking radiation, photons and other particles produced at the event horizon. This is the only light in the universe during the black hole era. The sky is not completely dark. It is lit by the faint, cold Hawking glow of countless evaporating black holes. As each black hole reaches the end of its evaporation, the process accelerates. The black hole shrinks. As it shrinks, its temperature rises. Smaller black holes are hotter, not cooler, and the rate of Hawking emission increases. The final moments of a black hole's evaporation, when it has shrunk to roughly the Planck mass, about 22 micrograms, are explosive by black hole standards. The last remnant of mass energy radiates away in a final burst of radiation. A brief flash of all particle types allowed by physics. And then the black hole is gone. Not consumed. Not collapsed into something else. Gone. The mass and energy transformed entirely into radiation and particles, dispersed into the expanding universe. The largest black holes go last. The sun-mass black holes evaporate first, at around 10 circumflex, 67 years. The galactic center black holes, the supermassive ones, evaporate somewhere between 10 circumflex 87 and 10 circumflex 100 years, depending on their mass. And when the last one is gone, when the final quantum of mass energy that was a black hole has been converted to Hawking radiation, the black hole era ends. What remains after the last black hole evaporates is the raw material of the universe. Photons at near absolute zero temperature, electrons and positrons moving at low velocities, neutrinos streaming through space, gravitons, if they exist as particles. These particles are essentially non-interacting at the extremely low energies and densities of the far future. They expand, they cool, they separate, and they continue to do so forever. The universe in this state has maximum entropy. There are no temperature gradients, no free energy, no structures at any scale. Every possible thermodynamic reaction has reached equilibrium. The laws of physics continue to operate. Nothing is suspended, but there is nothing for them to operate on in any interesting way. The universe is in its final state. This is the dark era, the universe after the last black hole. The dark era begins when the last black hole evaporates and extends forever. There is no end to the dark era. There is no second act. There is no phoenix from the ashes, no collapse and rebound, no new Big Bang arising from the cold remnants of the old one. There is simply an ever-expanding, ever-cooling, perfectly homogeneous gas of fundamental particles, growing more and more diffuse as the expansion of space continues to separate them. The temperature of this gas approaches absolute zero asymptotically. It never quite reaches zero. Quantum mechanics forbids a truly zero-temperature state. But for every practical purpose, the universe in the dark era is at absolute zero. The photons that were Hawking radiation from the last black holes have been redshifted by the expansion to wavelengths comparable to the size of the observable universe. The electrons and positrons occasionally meet and annihilate, producing two more photons. But these events become rarer and rarer as the particles are separated by the expansion. Is the dark era truly the end? In the most literal physical sense, the answer depends on physics we don't fully understand. If protons don't decay, if the proton is genuinely stable as some theories predict, then the degenerate era never fully ends. White dwarfs and neutron stars persist as structures. Over 10 circumflex 1,500 years, quantum tunneling effects may gradually transform the composition of white dwarfs. Carbon and oxygen nuclei tunneling into iron. Element 26, the lowest energy state per nucleon. Over 10 circumflex 26 years, even more exotic tunneling events could transform the cores of neutron stars. Black holes might form from white dwarfs over inconceivable timescales, via quantum processes that don't require proton decay. But these timescales are so large that they defy any meaningful comparison. The number 10 circumflex 26 is not a number in the ordinary sense. It is a googol raised to the power of 1,000,000,000,000. Writing out its decimal representation would require more digits than there are atoms in the observable universe, multiplied by itself several times. The universe in that era has expanded to a size that makes our observable universe 93 billion light-years across, containing 2 trillion galaxies, look like a proton compared to a basketball court. And yet the physics doesn't care about our inability to comprehend the numbers. The laws of thermodynamics operate. Quantum mechanics operates. General relativity operates. These laws have no off switch. They run forever, applied to a universe that has, in any humanly meaningful sense, already ended. The equations continue. There's simply nothing interesting to plug into them. There is one theoretical concept worth mentioning here: quantum fluctuations. Quantum mechanics predicts that even in a perfect vacuum, even in a state of maximum entropy with no particles, there are fluctuations. Virtual particles appear and disappear on timescales consistent with the uncertainty principle. In an infinite future, with infinite time, sufficiently rare quantum fluctuations could produce, occasionally, small regions of low entropy. Boltzmann brains, isolated, disembodied, momentarily conscious quantum fluctuations, are a theoretical curiosity in this context. By pure probability, given infinite time, random quantum fluctuations could assemble a configuration of matter that for a brief moment has the structure of a brain and experiences a moment of consciousness before dissolving back into disorder. This is not a prediction of what will happen. It is a calculation of what, in infinite time, cannot be ruled out. The Boltzmann brain concept is mostly discussed as a test of physical theories. Any theory that predicts more Boltzmann brains than ordinary observers like us is probably wrong, because we are clearly not Boltzmann brains. But it illustrates that the dark era, while dead by any functional standard, is not zero by any physical standard. The universe never reaches a final state in which literally nothing happens. It reaches a state in which nothing happens on any timescale we can conceive of. It reaches, for all practical purposes, the end. And that is the real end of the story of our sun. Not the planetary nebula, beautiful as it will be. Not the white dwarf, slowly cooling. The real end is a universe that has exhausted its potential for structure, for complexity, for the kind of organized matter that can measure time passing and notice that it's doing so. A universe that once contained our star, our world, our oceans, our species, and all we ever made. Now a cold, dark, perfectly uniform emptiness, still operating under the laws of physics, still technically existing, but silent in every way that matters. We've followed the sun to its death. Now let's follow Earth, or what's left of it. If Earth survives the red giant phase, if the combination of orbital expansion from solar mass loss and the exact maximum radius of the red giant sun leaves Earth just outside the stellar envelope, then Earth in the aftermath will be a dead rock. Not destroyed, not vaporized, still a planet, still orbiting a stellar remnant, still there, but transformed beyond recognition. During the red giant phase, Earth's surface will have been heated to thousands of degrees. The atmosphere, long since stripped of its nitrogen, oxygen, water vapor, and carbon dioxide by the sequence of events over the preceding billions of years, will have any remaining trace gases blasted away by the intense radiation and strengthened stellar wind. The oceans, already gone for billions of years, will be a distant memory. The surface rocks will have partially melted and resolidified multiple times. The crust will be a glass-smooth, oxidized, silicate surface. When the red giant phase ends and the white dwarf forms, Earth will orbit a white dwarf at approximately 2 ATU, its orbit having expanded from the current 1 ATU as the Sun shed roughly half its mass. The white dwarf is initially hot and bright, bathing Earth in UV and X-ray radiation. But it is small, Earth-sized, and its total luminosity is far less than the main sequence suns. Even close to the white dwarf, Earth receives far less total energy than it does from the current Sun. As the white dwarf cools over billions of years, Earth's surface temperature drops to near absolute zero. The rock is cold. The sky is lit by the faint glow of the cooling white dwarf and the distant light of other stars, other stellar remnants in the galaxy, other white dwarfs and neutron stars, and cold brown dwarfs. Earth is a frozen, airless ball of rock and iron, drifting in a cold and increasingly empty galaxy. The white dwarf itself, in the far future, may consume the remains of its planetary system. This is not speculation. We observe it happening around other white dwarfs today. About 25 to 50% of all observed white dwarfs show pollution in their spectra, signatures of heavy elements like calcium, silicon, magnesium, and iron that should have settled out of the atmosphere given the extremely high surface gravity. The explanation: these white dwarfs are actively accreting material from their surrounding planetary debris. Asteroids, rocky fragments, perhaps small moons, drawn in by gravitational perturbations and tidal forces, spiral into the white dwarf and are consumed, leaving their chemical signatures in the stellar atmosphere. The white dwarf, that was the Sun, will likely consume some of the rocky debris of the inner solar system, the remnants of Mercury, the fragments of asteroids, perhaps pieces of Earth's outer layers if they were disrupted during the giant phase. Earth itself, if it survives as a body, is large enough that its orbit may remain stable against being tidally disrupted for billions of years. But gravitational perturbations from the outer solar system, Jupiter and Saturn, which will have survived largely unchanged through the Sun's giant phases, will gradually modify the orbits of inner solar system remnants. Some will be scattered inward and consumed by the white dwarf. Some will be scattered outward and ejected from the system entirely. Over trillions of years, during the degenerate era, the Sun's white dwarf system will gradually lose its bound objects. The outer planets, Jupiter, Saturn, Uranus, Neptune, still roughly intact, may be gradually scattered away from the white dwarf by gravitational interactions with passing stars or with each other. The galaxy is not static. Stars pass through the solar system's general vicinity on timescales of millions of years. And over trillions of years, these encounters have significant cumulative effects. Earth, if it hasn't been disrupted or accreted by the white dwarf, may eventually be ejected from the Sun's system entirely, a frozen, dark, airless rock drifting through interstellar space, unbound to any star, for the remainder of cosmic time. A rogue planet, a cold remnant of the solar system, carrying in its rock the compressed, altered ancient signatures of the chemistry that once supported life on its surface. Or it may have been consumed by the white dwarf millions of years earlier. Its atoms spread through the stellar atmosphere in a chemical signature that would tell any observer, here was a rocky planet. Here was iron and silicon and magnesium. Here was a world. Either way, Earth's story ends in something much quieter than its beginning. not with catastrophe, not with drama, but with cold and dark and distance. The death of the sun doesn't affect only Earth. The entire solar system is transformed. Let's trace what happens to the other worlds. Mars, at 1.52 AAU from the Sun, will have a warmer future before things get worse. As the Sun brightens over the next 1 to 2 billion years, Mars, currently averaging minus 60 degrees Celsius, will warm. The permafrost and polar ice caps of Mars, which lock up substantial quantities of water and carbon dioxide, will begin sublimating. The Martian atmosphere, currently about 0.6% of Earth's sea level pressure, will thicken. As the sun brightens toward double its current luminosity over the next few billion years, Mars may briefly have surface temperatures above zero and a somewhat thicker atmosphere. This is the irony of planetary science. Mars is too cold today to support liquid water on its surface at most locations. In about 2 to 3 billion years, as the sun brightens and Mars warms, it may enter a brief window of relative habitability, not the lush, wet world it might have been in its youth, but a world where temperatures are above freezing for part of the year, where liquid water could exist in protected locations, where the atmospheric pressure is somewhat closer to what organisms might tolerate. This window will not last. As the sun continues brightening, Mars will eventually undergo its own version of Venus, a greenhouse runaway, though a weaker one given Mars's lower gravity and thinner initial atmosphere. During the red giant phase, Mars at 1.52 ATU will be inside the sun's extended atmosphere, probably inside the red giant's outer envelope for the period of maximum expansion. Mars will almost certainly be destroyed, evaporated, or severely disrupted by the red giant. Its orbit will have expanded somewhat as the sun loses mass, but the expansion won't be enough. Mars ends in the sun. Jupiter, at 5.2 ATU, is safely outside the maximum extent of the red giant. Jupiter's fate during the red giant phase is to be greatly irradiated. The luminosity of the red giant's sun, 2,700 times the current solar luminosity, will dramatically heat Jupiter's upper atmosphere, potentially accelerating the escape of hydrogen from Jupiter's atmosphere. Over millions of years of red giant phase, Jupiter may lose a significant fraction of its outer atmosphere. The effect on Saturn, Uranus, and Neptune will be progressively less severe with increasing distance. The ice moons of Jupiter, Europa, Ganymede, Callisto, and the others will be dramatically altered. Their ice surfaces, currently maintained near 100 to 130 Kelvin, will heat substantially under the red giant's 2,700 times greater luminosity. The surface ice will sublimate rapidly. The water vapor will be lost to space. If these moons have subsurface liquid water oceans, which current models suggest at least 3 of them do, those oceans may be exposed as the overlying ice disappears, before also evaporating under the intense irradiation. Saturn's rings, one of the most beautiful structures in the solar system, will be dramatically affected. The rings are made of ice and rock, primarily in a size range from centimeters to meters. Under the increased radiation of the red giant phase, the ice in the rings will sublimate. The rings will thin and eventually disperse entirely, either by sublimation or by absorption into Saturn's atmosphere. Saturn, without its rings, illuminated by a dim red giant sun, will still be visible as a planet, a banded oblate sphere, but it will look nothing like the Saturn we know. The outer solar system, Uranus, Neptune, the Kuiper belt, the Oort cloud, will be affected but less dramatically. Uranus and Neptune will lose some atmospheric hydrogen and helium. The Kuiper Belt objects, Pluto, Eris, Makemake, and the countless smaller bodies, will have their surface ices sublimated, briefly becoming active like comets as the red giant's luminosity heats them from dozens of AU away. The Oort cloud, extending to perhaps 100,000 AU, will be barely affected. After the red giant phase and the planetary nebula, Jupiter and Saturn will orbit the White Dwarf at 5.2 and 9.5 H2 respectively, their orbital radii expanded somewhat by the Sun's mass loss. They will orbit in the dark, slowly cooling for trillions of years. Lonely gas giants around a dead star, in a universe growing increasingly empty. Let's gather the full timeline in one place. From now to the end of everything. 600 million years from now, atmospheric CO2 falls below the threshold for C3 photosynthesis. Most plant life on Earth dies. The terrestrial food web based on photosynthesis collapses. Insects, birds, mammals that depend on plants, gone. Microbial life continues. 800 million years from now, CO2 falls below the threshold for C4 photosynthesis. All photosynthesis on land ceases. Oxygen in the atmosphere begins declining. Complex air-breathing life impossible anywhere on the surface. The planet is still habitable in its deep ocean environments. 1.1 billion years from now, the Sun is 10% brighter than today. The moist greenhouse effect begins. The stratosphere becomes wet. Hydrogen begins escaping to space. The ocean evaporation process begins. Life on Earth is now confined to the deepest ocean environments, protected from the increasing UV radiation by the thick, humid atmosphere above. 1.5 to 2 billion years from now, the oceans are largely gone. Surface temperatures are hundreds of degrees Celsius. The last life, extremophile microbes in hydrothermal systems, may persist, but the surface is sterile and extremely hostile. Earth is beginning its transition to a Venus-like world. 2 to 3 billion years from now, Earth resembles Venus today. Atmospheric pressure is elevated. Surface temperatures above 400 to 500 degrees Celsius. No liquid water anywhere. The planet is geologically active, but biologically dead. 4 to 5 billion years from now, the Andromeda Galaxy completes its merger with the Milky Way. The merged galaxy, sometimes called Milkomeda or Milkdromeda, has a chaotic structure for hundreds of millions of years before settling into a large elliptical galaxy. The Sun and its system, already in the outer regions of the Milky Way, may be flung to the outskirts of the merged galaxy during the interaction, or may be scattered into a new orbit within the merged system. The solar system survives the merger. The probability of a direct stellar collision is extremely low, but its location in the galaxy changes. 5 billion years from now, the Sun exhausts the hydrogen at its core. It begins the subgiant phase, brightening and slightly expanding. The red giant phase begins. Over the next several 100 million years, the Sun expands to 200 times its current size. 5.4 billion years from now, the Sun reaches its maximum red giant extent, somewhere between 1 and 1.5 ATUs in radius. If Earth still exists, it is either engulfed or inside the Sun's outer atmosphere. Mercury and Venus are certainly destroyed. 5.4 billion years from now, the helium flash. The degenerate helium core ignites in a brief explosive event, releasing enormous energy in the stellar interior. The Sun settles onto the horizontal branch and burns helium stably for about 100 million years. Approximately 5.5 to 7 billion years from now, the Sun completes the asymptotic giant branch phase, experiencing thermal pulses and losing mass rapidly in a strong stellar wind. The outer layers are expelled. A planetary nebula forms. 7 billion years from now, the planetary nebula disperses. The White Dwarf, 0.54 solar masses, roughly Earth-sized, begins its long cooling. 100 trillion years, 10 circumflex 14 years. From now, the last red dwarf stars die. The stelliferous era ends. The degenerate era begins. 10 circumflex, 32 to 10 circumflex 40 years from now. If proton decay occurs, all ordinary matter dissolves. White dwarfs and neutron stars evaporate. The degenerate era ends. 10 circumflex 67 years from now. Stellar mass black holes finish evaporating via Hawking radiation. 10 circumflex 87 years from now. Supermassive black holes, like Sagittarius A, complete their evaporation. 10 circumflex 100 years from now. The last most massive black holes, ultramassive giants, finish evaporating. The black hole era ends. The dark era begins. After 10 circumflex 100 years, the universe is a cold, dark, perfectly uniform gas of fundamental particles, expanding forever, cooling forever, never again forming any structure. This is the timeline of everything, from the Sun today to the last black hole. The span of time from now to the end of the black hole era is so incomprehensibly vast that the current age of the universe, 13.8 billion years, is an infinitesimal fraction of the beginning of the story. We are in the first blink. The picture I've painted so far is of a universe going smoothly from bright and energetic to dark and cold. And that's broadly correct. But the details of the intermediate stages, the degenerate era especially, are more interesting than a simple fade to black. As the stelliferous era winds down and the last main sequence stars exhaust their fuel, something counterintuitive sometimes happens. New sources of energy emerge in unexpected places. Not enough to reverse the overall trend toward maximum entropy, but enough to create temporary warm spots in an otherwise cold universe. Brown dwarfs, objects between roughly 13 and 80 times the mass of Jupiter, too massive to be planets but too low mass to sustain hydrogen fusion, cool slowly over trillions of years. The most massive brown dwarfs, at the top of the mass range, can sustain limited deuterium burning for perhaps 100 million years at formation, and some can sustain lithium burning. But these are brief phases. After the burning stops, a brown dwarf is essentially a cooling sphere of degenerate gas. However, during the early degenerate era, something interesting can happen. Brown dwarfs can collide and merge. With the stelliferous era over and no new star formation, the population of brown dwarfs is fixed and slowly dispersing. But over very long timescales, gravitational interactions in star clusters and the remnant gravitational wells of former galaxies can occasionally bring two brown dwarfs together. If the collision is gentle enough to result in a merger rather than a destructive impact, the merged brown dwarf may exceed the hydrogen fusion threshold. A new star, briefly, ignites. These collision-born stars are called reborn stars in the speculative astrophysics literature. They would be faint, small, and short-lived by main sequence star standards. but they would be points of light and warmth in an otherwise dark era. Their lifetimes would be short, perhaps a few billion years for the most massive, before they exhaust their fuel and fade. These collision-born stars represent the last flickers of stellar light in the universe, brief and improbable, emerging long after the natural end of the stelliferous era. More exotic still is the fate of the universe's dark matter. Dark matter constitutes about 27% of the total energy content of the universe. We don't know what it is. If dark matter is made of weakly interacting massive particles, WIMPs, then WIMPs, like all particles, can be their own antiparticles. In regions of high dark matter density, WIMP annihilation produces high-energy photons and other particles. This is a potential energy source in an otherwise dark universe. During the degenerate era, dark matter continues to fill the universe. If it accretes preferentially in certain locations, the centers of former galaxy clusters, for instance, or around the most massive stellar remnants, the local dark matter density in those regions could be high enough to produce significant annihilation radiation. This would create tiny warm spots in the cold universe, regions where the annihilation of dark matter into radiation provides a faint energy source that slows the cooling rate of nearby objects. This is not well understood. We don't know if dark matter is WIMPs. We don't know the cross-section for annihilation if it is. The details of how dark matter behaves over these timescales are highly uncertain. But the principle that there are potential energy sources in the degenerate era beyond the simple cooling of ordinary matter is real and worth knowing. The universe finds its resources in unexpected places. Even as everything tends toward cold and dark, there are processes operating at the edges of our knowledge. Collision-born stars, dark matter annihilation, quantum tunneling, that create temporary local reversals of the overall trend. They don't change the outcome. The outcome is the dark era, but they make the journey more interesting than a simple dimmer switch being turned off. The universe doesn't die all at once. It dies piece by piece, in different ways in different places, over timescales ranging from billions to trillions to googolls of years. Our sun is one piece. The last red dwarf will be another piece, trillions of years from now. The last black hole will be the final piece. And between all of those deaths, the physics finds corners of warmth and briefly inhabits them, before they too fade. This is the nature of a universe governed by the second law of thermodynamics. Entropy always increases, but it increases at different rates in different places. The path to maximum entropy is not a highway. It's a landscape with hills and valleys, local reversals and global trends, brief islands of order in an ocean of growing disorder. The question comes naturally. If life on Earth has roughly 1 billion years before the sun's brightening makes the surface uninhabitable, can life, technological, intelligent, capable life, do something about it? Can it survive the sun's death? In principle, yes. And this is not mere speculation. The physics allows for several mechanisms by which a sufficiently advanced civilization could extend the habitable window, change its location in the solar system, or even migrate to another star system entirely. The most commonly discussed long-term survival strategy involves changing Earth's orbit. Earth is currently at 1 AU. If Earth could be gradually moved outward to 1.5 ATU, then 2 AU, tracking the sun's expanding habitable zone as the sun brightens. It would remain at a roughly constant temperature even as the sun brightens. The energy required to move a planet the mass of Earth is enormous but not infinite. Gravitational assists, using comets or asteroids on carefully calculated trajectories to slowly transfer momentum to Earth over millions of years, could in principle accomplish this over geological timescales. The timescales are long, but the physics is not forbidden. A civilization capable of executing planetary orbital engineering would also likely be capable of more dramatic interventions. Stellar engineering, modifying the sun's output or mass loss rate to extend its main sequence lifetime, has been proposed theoretically. One concept, called stellar lifting, involves using electromagnetic forces or directed beams to remove mass from the sun's outer layers, reducing its mass and therefore its luminosity, and extending its main sequence lifetime. A less massive sun burns more slowly and lives longer. By removing mass gradually over billions of years, you could potentially extend the sun's main sequence lifetime by several billion years. These are not technologies we have. They are not technologies we can predict with any certainty. But they are technologies the physics permits. The laws of physics as we understand them do not prohibit a civilization that has had 1 billion years to develop from achieving capabilities of this kind. 1 billion years is a very long time. Modern human civilization is about 10,000 years old. We have gone from stone tools to spaceflight in 10,000 years. Extrapolating another 1 billion years is essentially impossible. The end point is beyond any prediction we can make. But the direction of travel toward greater technological capability, greater energy mastery, greater ability to shape physical systems on larger scales, seems robust across the history of complex life on Earth. If a civilization survives and continues advancing for 1 billion years, the question of whether it can survive the death of its star is almost certainly a question that civilization will have the capability to address. The more pressing question, the one that matters on shorter timescales, is whether any civilization will survive long enough to need to address it. For Earth life, the bottlenecks are not primarily astronomical. The astronomical threats are real, but distant. The immediate challenges, climate change, resource constraints, technological risk, political coordination across a global civilization, are the relevant ones for the next few hundred years. If we navigate those, the billion-year timescale of the sun's brightening becomes a future problem, not an immediate one. For what it's worth, the universe is structured so that the primary threats to any given biosphere come from the star that supports it, on timescales of billions of years. The physics is generous in that sense. It gave life on Earth a window of at least 1 billion years to develop from single cells to technological civilization to whatever comes next. Whether the next several hundred years close that window early, or whether the window remains open long enough for something extraordinary to pass through it, is not determined by astronomy. It's determined by choices. The death of the sun is real. The timeline is specific. The physics is understood. But the response to that knowledge, what we do with the 1 billion years of window that remain, is entirely open. The reason we can be specific about the sun's future, why we can say in 1.1 billion years the oceans begin evaporating, rather than at some point things will get bad, is that we can observe the deaths of other stars in real time. The sun is an ordinary star. There are hundreds of millions of stars in the Milky Way with similar masses, similar compositions, and similar ages to the sun. These stars are at different stages of their lives. Some are younger than the sun, some are in the subgiant phase, just leaving the main sequence. Some are red giants right now. Some have already completed their red giant phase and are white dwarfs, and some are at every intermediate stage. By observing all these stars, by measuring their luminosities, temperatures, sizes, compositions, and behaviors at different stages, we build an empirical picture of stellar evolution. We don't have to wait 5 billion years to see what the Sun will look like as a red giant. We can look at Aldebaran, a red giant star about 65 light-years away, with a mass of about 1.7 solar masses, in the red giant phase right now. We can measure its spectrum. Its size, it's about 44 times the Sun's current diameter. Its temperature, about 3,900 Kelvin. Its luminosity, about 440 times the Sun's. And we can say, this is roughly what a star of similar mass to the Sun looks like in the red giant phase. We can look at Betelgeuse, a much more massive star, about 16 to 19 solar masses, in the red supergiant phase, and observe the enormous mass loss occurring in real time. Betelgeuse is losing mass at a rate of about 10 circumflex 6 solar masses per year, expelled in clumps and shells that we can observe as thermal infrared emission from warm dust. The patterns of mass loss from stars like Betelgeuse inform our models of mass loss from solar-type stars in their giant phases. We can look at planetary nebulae, the expelled shells of stellar material from stars that completed the giant phase, and measure their compositions, their expansion velocities, their morphologies. The Ring Nebula in Lyra is a planetary nebula from a star of roughly solar mass, and by measuring its properties, we constrain what the Sun's own planetary nebula will look like. Its inner ring is about 0.6 light-years across. Its central white dwarf, still hot, ionizes the surrounding gas. Its expansion velocity is about 20 kilometers per second. These are numbers we can use. We can look at white dwarfs of different ages and measure their temperatures, using the physics of cooling to determine how long they've been cooling. The Hyades cluster contains white dwarfs about 700 million years old, and their temperatures constrain the white dwarf cooling rate at that age. The globular cluster, NGC 6752, about 13 billion years old, contains white dwarfs so old that they've cooled to below 5,000 Kelvin, visible only in the infrared. We can look at systems where white dwarfs are accreting material from companion stars or from the debris of disrupted planetesimals, and measure the composition of that accreted material from the spectral lines it leaves in the white dwarf atmosphere. These measurements tell us about the compositions of rocky planets and asteroids that were disrupted, and they reveal compositions that look remarkably like the rocky bodies in our own solar system. Earth-like chemistry is common. Rocky planets with iron cores and silicate mantles are common. The kind of world that supports life is not an aberration. All of this observational data feeds into stellar evolution models that have been refined for 80 years. The models are not perfect. There are open questions about mass loss rates, about the dynamics of the asymptotic giant branch, about the exact maximum radius of a solar-type red giant. But the broad structure is well understood. The timeline I've given you tonight is the consensus of decades of stellar physics research. The Sun is not a mystery. It is a problem that's been largely solved. And the solution is the story of tonight. There is something unusual about the human situation when it comes to the death of the Sun. We know it's coming. We know the timeline. We know the mechanism. We can see it in the deaths of other stars around us, happening right now, at different stages. We are uniquely positioned to look at our own star and say, in 5 billion years, It will be a red giant, and here is exactly what that will look like. No organism in the history of life on Earth, until us, could have known this. Not the first multicellular organisms in the Cambrian, not the first land plants, not the first birds, not our hominid ancestors. Every organism that has ever lived on this planet lived in ignorance of the sun's future. They lived in the warmth of the present, without any awareness that the warmth was finite. We know it's finite, and this knowing is a gift, not a burden. It is a gift because it contextualizes everything. The fact that the sun has 5 billion years of main sequence life remaining, that life on Earth has roughly 1 billion years of window before the brightening becomes catastrophic, tells us that the project of life, of civilization, of intelligence and culture and science is not a brief, accidental flicker. It is a potentially very long story. The story so far, about 4 billion years of biology and 600 million years of complex life, and 300,000 years of Homo sapiens, represents a tiny fraction of the window. The story isn't close to over. It is also a gift because it reveals the continuity of things. The sun was made from material that was previously inside other stars. The planetary nebula it will produce in 7 billion years will enrich the interstellar medium with carbon and oxygen, which will eventually become part of new stars and new planets. The atoms in your body right now, in your lungs and your blood and your brain, will, in some form, participate in everything that follows. Not you as a conscious entity, but the atoms that compose you have been through stellar cores before and will go through stellar cores again. The timeline of the sun's death is also, in a way, a timeline of the universe's generosity. It took 9 billion years of prior stellar generations, stars living and dying, and enriching the interstellar medium with heavier elements, to produce a molecular cloud with enough carbon and oxygen and iron and silicon to make a rocky planet like Earth. Then another 4.6 billion years for Earth to cool, for life to emerge, for evolution to produce complexity, for intelligence to arise. The sun's 10 billion year main sequence lifetime was necessary, barely necessary, for this process to occur. A shorter-lived star would not have provided enough time. A longer-lived star would have been less massive, with a cooler surface, perhaps less suitable for the photochemistry that drives biology. The sun is the right kind of star. Its lifetime is calibrated not by any intentional design, but by the laws of physics, to just barely allow the emergence of the kind of complexity we represent. That calibration is itself worth marveling at. The universe's generosity has limits. The window closes. The sun will die. The planets will be incinerated or frozen. The last stars will exhaust their fuel. The black holes will evaporate. And the dark, cold, perfect silence of maximum entropy will follow. But between now and then, in the specific 5 billion year precisely understood window between the current sun and the red giant that destroys Earth's orbit, there is time. Time for everything that life can become, everything that mind can discover, everything that the universe can produce from the kind of organized matter that has the audacity to look up at its own star and ask what that star's future holds. We are living in that time, right now. Tonight, the sun will set tomorrow morning, having generated during the hours of this night alone about 10 circumflex 41 joules of energy. It has been doing this for 4.6 billion years. It will do this for 5 billion more years before anything significant changes. There's time. Let's come back to the present. The sun rose today. it will rise tomorrow. For the next 100 million years, a span of time that contains the entire history of primate evolution several times over, the sun will rise and set in a way that would be indistinguishable to any observer from the sun of today. No change in color, no change in apparent size. A very slight increase in brightness, too slow to perceive on any human timescale, detectable only by comparing very precise measurements across millions of years. The sun you've seen today is not a star in decline. It's not noticeably aging. It is in the middle of a long, stable, luminous life. The hydrogen at its core is abundant. The fusion proceeds at its measured pace. The photosphere radiates at 5,778 Kelvin. The solar wind streams outward. Everything is working exactly as it has been working for 4.6 billion years. And somewhere in the sun's core, the photons being generated right now by nuclear fusion reactions will spend about 100,000 years working their way to the surface, being absorbed and re-emitted millions of times as they random walk through the dense solar interior. The sunlight that hits your skin tomorrow morning contains energy that was generated in fusion reactions occurring somewhere around the year 98,025 BC. Before the invention of agriculture, before the development of anatomically modern humans, before Homo neanderthalensis fully diverged from our lineage. Ancient energy, arriving now, after 100,000 years of travel through the sun's interior. Tonight, lying in the dark, you are receiving the indirect products of those ancient reactions. The warmth in the room, the air you're breathing, maintained at a hospitable temperature by a planetary climate system driven by solar energy. The food that fueled your body today, grown by photosynthesis that captured solar photons. The neural activity in your brain right now, processing these words, that activity ultimately runs on the chemical energy in your neurons, which came from food, which came from the sun. You are, in a very literal physical sense, made of sunlight. The sun's energy flows through you, transformed from photons to glucose to ATP to the electrical signals in your nervous system that constitute thought and awareness. You are a piece of the sun's output, organized into a temporarily complex structure that can contemplate the sun's future. In 5 billion years, the sun will be a red giant. Earth, if it still exists, will be an incandescent rock. The oceans will have been gone for nearly 4 billion years by then. Whatever was here, whatever biology, whatever civilization, whatever culture, whatever knowledge, will either have survived by moving elsewhere or will be gone. But that is 5 billion years from now. On any time scale that matters to a living human being, those 5 billion years are effectively forever. The sun is stable. The earth is habitable. The window is open. What passes through that window, what emerges from this planet and this civilization and this extraordinary, unlikely brief experiment in organized matter, is not written yet. The stars we see tonight are the same stars that watched the first humans look up. Some of them are older than our sun. Some will outlive our sun by trillions of years. Some are red giants right now, their inner planets engulfed or incinerated, exactly as Earth's will be in 5 billion years. Some are white dwarfs, cooling. Some are neutron stars, spinning. Some have planets, and some of those planets may have life, and some of that life may be looking back across the dark at the same stars we see. We are inside a universe that is alive, in the sense that matters, alive with fusion and radiation and gravity and chemistry, organized at 100 scales simultaneously, building complexity in the brief windows that its thermodynamics allows. Our sun is one of the universe's living things. It was born, it is burning, and it will die. And in the interval between its birth and its death, this particular corner of the cosmos produced you. That is worth something. Maybe everything. The sun has 5 billion years left on the main sequence. The window is open, the light is on. Sleep now. The sun will set in a few hours and rise again, reliably, for several billion more years. Nothing tonight requires anything from you. The universe continues. Good night.